Hello everyone, thank you for joining us. My name is Shotab Zedi,
And my name is Mushur Rahman.
and in today's presentation we will be talking about engine control strategies with functional safety ISO 26262. This is something we have learned during our course at LHPU. But before going over the presentation, just go over our background. So I did my Bachelor of Science in Mechanical Engineering from Colorado State University. For my senior design project, I worked with Caterpillar on their natural gas engine to test the phenomena of supernovae. I have skills in Simulink, MATLAB, and ANSYS and SolidWorks.
And I graduated from Florida Institute of Technology with a Bachelor of Science in Mechanical Engineering. My senior design project was funded by ASHRAE, and we had to develop a predictive cooling model. I have experience with MATLAB, Simulink, ANSYS, and Workbench.
All right, let's talk about the overview and background first. So let's talk about the embedded system. So embedded system is the computer system which is commonly used in vehicle nowadays. This system is very cost effective and efficient as it is a computerized method of controlling your vehicle and there is no manual interference. So the goal of the project was to implement the embedded control system into the Cummins 5.9 liter i6 diesel engine while making sure the functional safety standards. But before we can actually perform the engine testing, it was important to go over some basics and understand how the process and networking works. So we did a project on understanding of the CAN communication, electronic throttle control, and distribution control system. Also, we work on the engine controller and develop minimum max governor, and we perform hill testing. And after we got the result from the hill testing, we went over the actual engine testing. Now, Mashur will talk about the CAN communications.
So CAN communications is an essential part to understand how components in a vehicle function with each other and communicate with each other. CAN communication basically ECUs or electronic control units, which take care of each part of the car, communicate with each other via the CAN bus, which eliminates the need of any host computer. And what this does is it allows for faster access between ECUs and faster data transfer between ECUs, and it allows ECUs to communicate with each other simultaneously and send messages simultaneously. So during CAN communication, we learned about CAN data frames, we learned about CAN protocol, and one of the protocols which is currently used in the real world is the J1939 protocol, which we studied in our course. And in this J1939 protocol, there are various layers like the data link layer, transport protocol, application layer, diagnostic layer, network management layer, and each of these are essential to identify problems, either problems or to understand where the data is coming from. So one of the key aspects of J1939 that we learned was to read message ID of the extended message data frame. So J1939 is an extended data frame which uses 29-bit CAN identifier, and our task at the first week was to understand how to read these messages in order to identify where the messages are coming from, where the message is being sent to, and from these messages we can find the parameter group number. So this parameter group number specifies from where the problem is occurring or where to look for the problem, and the suspect parameter number we can identify from the parameter group number, which allows us to find the actual values. So parameter group number usually is sent in bytes and bits, and our job as the user at the first week was to try and decode these bytes and bits to real values, which the suspect parameter number allows us to. Moving on to the next slide. So this is our first actual project on electronic throttle controller. So in this project, our task was to create Simulink model with Motorhawk, where we'll have a PID controller, and using this PID controller, we have to control the electronic throttle controller, ETC. So the ETC takes throttle position sensors. At the top picture on the right, you see that it's the sensors are the TPS sensors and the slider. AP slider percent, which will in our real engine will be our pedal. But since it's at the initial testing phase, we are using a linear potentiometer to mimic the pedal. And these data will be sent to the controller, where we'll have a PID controller. The PID controller essentially allows us to control the stability and of the electronic throttle controller. P stands for proportional, I stands for integral, and D stands for derivative. The proportional controller controls the reduces the rise time. The integral controller reduces the steady state response, and the derivative controller reduces the steady state error, and the derivative controller reduces the transient error. So using this data, we flashed to MotoTune, and from MotoTune, we had to calibrate the accelerator pedal position, and we had to calibrate P proportional, integral, and derivative gains in order to stabilize and reduce our overshoots or instabilities in our electron throttle controller. There is a video on the right which we are playing now. So as you can see, this is our final product. When we after all our testing was done and our calibration was done, when we moved our pedal, we saw that there is no instabilities, there was no overshoots, and there was no lag between input and the electronic throttle controller, which means our setup was successful. But before this, when we were trying to calibrate that, we had to do a lot of troubleshooting, and we definitely had a lot of overshoots. So moving on to the next slide, we have the distributed control system. So in distributed control system, we are basically learning how to implement CAN alongside with our ECUs. So distributed control system allows us to communicate between ECUs via CAN wire. So if you see the picture on the right, there is a blue and white wire, which is the CAN wire, and via this CAN wire we'll be controlling the communicating between the two ECUs. So on the left, we see there is a team A ECU, team B ECU. So one of the ECUs will have the PID controller, and will send the duty cycle percent to control and to enable the electronic throttle controller. The electronic throttle controller in the team B's ECU will be sending the throttle position signals and the pedal signals back to the PID controller to complete the process. And our main thing that we had to take away from this project is how to write the MATLAB script files, and how these MATLAB script files allow the both ECUs to communicate with each other. So in this MATLAB script file, we had to write how team A's ECU will receive the signals, and how team B's team B ECU will read the signal, and vice versa. So moving on to the next slide, we have functional safety standards. So one of our goal of this course is to implement functional safety standards into our testings. So we use our functional safety standards on our electronic throttle controller. So for example, we had a functional safety goal on the ETC, which was to prevent unintended acceleration. If there is an unintended acceleration, there might be accidents, or there may be accidents or other damages. So to do this, ISO 26262 has given us certain prevention strategies so that unintended acceleration doesn't occur, such as when we switch on the electronic throttle controller, the electronic throttle controller valve will do a full sweep, so that we know that the electronic throttle controller is responding properly. In brackets, I have written PBIT, which stands for power on bit, means it will only happen when the power is switched on. Another prevention strategy is we have to when the process is ongoing, the throttle valve ETC will communicate with the accelerator pedal position, and that's why it's written in brackets C bit, which stands for continuous bit. So this will be an ongoing process during the actual program. So our last prevention strategy which we used was that if there is any failure in the hardware and software, the throttle position will come back to 10 to 15%, which allows for some fuel to still be going to the engine, so that the user can control the vehicle if there is any hardware software failure. So according to these things, we have found in ISO 26262 that this specific functional safety goal is classified as asset level B, and this asset level is determined by the picture on the bottom. So exposure, probability of exposure, controllability, and severity of failure. Moving on to the next slide, Shozab will be talking about minimum and maximum governors.
All right, so let's talk about the minimum governor. So after our ETC project, we developed some learning about creating the engine controller. So for which we can develop the minimum and maximum governor. So let's talk about the minimum governor and what is it. So minimum governor is basically your idle controller. So it outputs the signals to the fuel pump at how much fuel will be needed for setting the RPM to the low speed position. For our MIL testing model in the loop, we use the set point of 700 RPM, and so this thing in real life, the way it works is when you crank start your car, the RPM goes up, and then it comes back and settle down at one position. So that is what a minimum governor do. It brings the RPM to the set point when the engine is running and when the pedal position when there is no uh, when you didn't push the pedal. So that's how it's sets over there. So for developing the minimum governor, we use the PIE controller. We use some other strategies like engine state manager, like we use stall states, crank state, and run state. This using these states helps to determine the governor, like where it needs to start working. And then we also use the set point manager and the feed forward. This helps with the uh, different conditions, like how when there is a cold start or any other situation, how the governor will act over there. And it also helps like the governor to work dynamically, not increasing suddenly the fuel injection and not lowering the fuel injection suddenly. Over here, the graph shows you crank start your car, the, we the crank start of the engine, and then it goes up to 700 RPM. And when we start the slider again and we increase the RPM, it goes up in a pretty good manner. And when we release it, it comes back to 700 RPM. So it shows over here that the minimum governor is working in the MIL testing. So now let's talk about the maximum governor. So maximum governor is pretty much same as the minimum governor. Uh, it it also sends the output signals to the fuel pump, and it outputs the signal of the fuel injection, and it tells the fuel pump that how much fuel will be needed or how much fuel reduction will be needed when the RPM goes to its maximum level. So over here we use the pretty much similar system which we use for the minimum governor. We attach the slider gain over here. Some of the different strategies we use over here was the entry threshold manager, because this threshold manager make sure that when the maximum governor needs to start working and when it's need to stop working. And we use the initial condition as well to make sure what was the actual position when the maximum governor starts working. We use different loads to run on that. Over here, the graph shows when the car start, the smooth straight line shows the car is on the minimum governor, and then when the slider gain goes up, it reaches to the maximum point, and when we move slider gain back, it comes back to the minimum set point. So this is a very good representation from the MI testing, which shows how the maximum governor is working here. Let's move on to the hill testing.
So the hardware and loop testing is an essential part before we actually do the real engine testing. So in the hardware and the loop testing, we will be using an actual pedal position instead of our slider gain, because this actual pedal position will be giving us a more accurate real life information compared to a slider gain. So our task in this hardware and loop testing was to calibrate this accelerated pedal position and to check if our minimum and maximum governors are working alongside with our pedal position. So we had our same minimum and maximum governor model, and we implemented this. Alongside alongside with our accelerated pedal position. So there is an oscilloscope to the right, or in the video we'll see later. So this oscilloscope video will show us the yeah. So you see that there is a graph, and you can see there's an up and down of voltage. That is a duty cycle signal that is being sent when we press the starter switch.